Shigenori Nakatsuka, même si the title is Duality of W-superalgebras.
Very much as that for introductions, and I'm very happy to attend this conference and chat with people from probability theory or physics people, who I don't meet in my usual life. So I'm very enjoying this conference, and thank you very much for invitations. Today, so first of all, my profile is an algebraic guy working on CFT as a mathematician, and for me, CFT 2D calculus that I don't write is a study of representation theory of conformal algebras in one dimension on complex domains. So it's a Piazzolo the algebra at central charge C, which is generated by these functions and which has expansions in this form. And why this is relevant to the conformal things is this operator is this case on this algebraic vector field over the complex curve, so which is a infinitesimal conformal transformations. And Piazzolo is a central extension of this vector field. Yes, so, and this is called Piazzolo vertex algebra. And in the 80s work by Polyakov, these people try to understand, formulated CFT in terms of representation theory of Piazzolo vertex algebras, and they thought about the minimal models. Which means that it's very minimal as a physics theory, meaning that we don't have a lot of fields, and all the universal one will be quotiented out to getting a really minimal state, minimal vector space. And in other way to say during this conference is that it is from a modular tensor category in these setups, or coming from a rational vertex. And here, tensor product is not a vector space tensor product where we can think about for the real algebras, but more vertex algebraic one or a field theoretic one, and thinking about pairs, and we consider a kind of inverse. We have a stated field correspondence. Where the product is locally a product of this very local disks, and we put several disks to take a product to going to the other side of these models. And here, everything's tensor product of these data expressed in terms of this vertex operator like ones, which is in general called intertwining operators. And the post-Feigin theory is deriving the braided tensor category structures by transforming a point where we put the modules by using the transformation coming from these ones to gain the tensor product and also the braiding isomorphism to obtain rich information on the representation theory. But most important, their data is all coming from the analytic behavior of these intertwining operators realized on this CP1 or compact Riemann surface in general. So this is a kind of 80s works, and quickly CFT is also has a super CFT, which is a super generalizations, where we have a bunch of physicists found one by one many kinds of extensions of conformal algebras, and they are called n=1 super-conformal algebra, 2 super-conformal algebras, and so on and so forth, meaning that we have an extension of odd fields of these given numbers. And so we are also interested in the minimal models of this super-conformal field series, meaning that where we can get modular tensor categories, for example.
So I wonder if there's a natural stopping point for this sequence, or is it
so it's a good question. And 3 and 4, and we have basically 5 of them, but so we have kind of very specific names.
Still possible, right?
No, but we have a kind of a mixture of these superalgebras and this Virasoro to gain infinite many families. Where some mathematicians say that it's also a family of these super-conformal algebras. So that's why I put dots, and because it's infinite. So we can always thinking about the minimal model for each of them, but which is a kind of not the economical way to do play one by one. And one way to introduce W algebra is there is a uniform construction of all these guys by through the so-called W superalgebras. And so I will go back to this point at the end of my talk. But for the first time, for almost all my talk, I restrict myself to a much easier algebra called n=2 super-conformal algebras. So this is a new infinite dimensional these superalgebras, and we can play in the same game, but it is always convenient if we can realize it by using known ones, which you are familiar with. And convenient way is a so-called cosette realizations to attack this minimal models classification. So more explicitly, what this cosette realization talking about is we can realize this n=2 super-conformal algebra in terms of another infinite dimensional real algebra called affine vertex algebra of SL2 times differential operators on odd vector field or BC gauss, or we have a bunch of names. Maybe lattice vertex superalgebra associated with this lattice. But all these definitions are equivalent, so let me write in this way. And we have a embedding, which is uniquely determined by some properties. So I forgot to say about what this algebra looks like, but it's a extension of Virasoro, so it has a Virasoro and 2 odd vectors corresponding to this name, which I call G plus and G minus, which is odd ones. And we have additional Heisenbergers. And the realizations, and this algebra is uniquely generated by these 2 guys. And there's a unique realizations which maps these 2 fields to the quite obvious vertex operators. So basic idea is that we shift SL2 E and F by using an odd element. Then we can shift OPE slightly to get this G plus and G minus and generating the whole Virasoro superalgebras.
So they have dimension 3 alpha?
Yeah, 3½ yes. So 2 and 1. And so 1 and 1/2, very precisely. And as you can see, E is paired with X and F is paired with minus X. So we have a kind of easy symmetry which means that actually there is a kind of one diagonal Heisenberg vertex algebra embedded into two guys. Then if we collect all the states commuting with the actions of certain Heisenberg, then we get the isomorphism. So this is called a commutant or coset constructions of n equal to super-conformal algebras. And this is a very nice property because to gain modular tensor category, working on this universal Virasoro universal super-conformal algebra is a quite wide representation theory. So we control this by going down to the simple quotient of this vertex super-algebras. So simple quotient. Is uniform. And this realization is compatible with the simple quotient, and it is realized in terms of the simple quotient of affine SL2.
The simple quotient, is it just the singular vector in the Virasoro in a non-super Virasoro which you quotient by all?
Yes, and I don't know this is the all singular vector, but yeah.
Just generated by the even singular vector.
It has many singular vectors.
Yes, and subsingular, a lot of subtle things appearing in the superset things. And also it quite depends on the levels K, I think.
Yeah, of course,
So-
it depends on the level. If it's in church, yes.
Right.
So I cannot say very sure things, but one way to say that we don't have to care about too much by using this affine SL2. This is one message. Yes. Okay. So
We could say that how we define commutator is just all operators commuting with this Heisenberg, or
yeah, exactly. And this is a very specific one. So if we want to write first one times J. I didn't say about what is J, but there is a standard normalization, then we can realize this.
what is delta?
Delta is a diagonal Heisenberg.
Diagonal Heisenberg.
Yes.
Diagonal Heisenberg. Yes.
Yeah.
It's also huge.
But this J is different than the charge in your n equals 2 theory.
Sorry?
Yeah.
J,
Two
yes.
different J's on the board.
No,
It's not your
this
charge
J
coming from
corresponding to.
Navier-Schwarz.
Oh, sorry. Oh, wait. Sorry, X. So which is a standard Heisenberg in this lattice.
Right.
Yeah, sorry. Thank you so much.
Mhm.
Okay.
Mhm.
And especially, we know one family that K is 0, 1, 2, 3 non-negative integers, where this affine vertex algebra gonna be rational, which is a analogy of finite dimensional representations of SL2 in the context of affine SL2. Then this coset theory immediately implies that this is gonna be rational as well. So this is power of the coset construction, and this was found around 80s, and because of this construction, physicists succeeded classifying the simple modules and all the important data. So, and actually, as you can naively imagine, from this construction, the fusion rule is a tensor product decompositions of these two affine SL2 and n equal 2 look similar. So, fusion rule. Should be similar. This expectation can be formulated in this way. So we have tensor categories of this bigger representation, which is equivalent to the affine SU2 representations because this is trivial theory. And we have on the other hand, we have a super-conformal algebra times Heisenberg that we use as a coset, which actually grows up to a certain rank 1 that is vertex superalgebra, and we can consider the representations which factors as a tensor product of these two guys actually. But important thing is that we have a induction factor, which is a tensor factor. Yes.
What is L again? You replaced your coset with V sub L.
It's a simple quotient.
Okay. Also, when you say the fusion ring should be similar,
Yes.
similar means isomorphic or?
No, and that I'm presenting in second.
Okay.
Thank you so much. So this tensor factor, this is an induction factor. So we have representations. Then, because we have a tensor structures, so we just inside with bigger algebras as a representations over this super zero times that is. And this gives us realizations of fusion rings of this guy in terms of this guy. Namely, so let me write fusions this way. It's isomorphic to the fusions of AK SU2, which is this side. And we have a lattice theory here. And this is taken to be carried here, in this case, to K+2. But we have a kind of redundancy here to cancel out unnecessary modules. So the fusion rings is realized in terms of in this description. So in terms of Biazoro and lattice theory by using some monodromy actions. And we can invert this formula in a very symmetric way, thanks to a construction theory. So I don't specify all the details, but like this. So yeah.
So what do you mean by the fusion ring? Is it just you keep the simple modules of
Yes,
the
so-
bosonic parts or
Bosonic.
I mean, the categories are semi-simple, right here.
Yeah.
so
So
what is the category? It's representations of the bosonic parts.
no. All the modules. But untwisted sector. What would say? Raman twisted modules.
Yeah,
I
so
don't
the
care about
Z2
that.
is to do with the parity.
Yes. So we consider category for as literally unique to super-conformal algebra, which is of course has a parity decomposition.
Right.
But we just keep the representation like that. Just weak representations, but finite regenerations.
So is it a fact then that on the one side you have both Nevis-Schwarz and Ramon sectors and you're just modding out to get the Nevis-Schwarz or something?
Sorry, say it again, please.
You have somehow on the left, you have Nevis-Schwarz and Ramon.
No, I don't care about the twisted sector.
But is that why you mod out by Z2 to just get the Nevis-Schwarz?
Yeah. In this case, yes. So we have a kind of intermediate part where we translate these twisted and untwisted sectors. As a category, it's isomorphic.
Right.
But as a fusion ring, we have a bit of extension things. Double.
So, but if that's the case on the, in the bottom line, is there any way of?
So
the
here,
twisting-
I don't care about the twisted sector, so it looks similar, but if we want to consider twisted sector, then we need to consider maybe twisted over here, which makes a compensation.
I see.
Yeah.
Okay.
So the other algebra is also super algebra, super VOE, the product of
okay, so important thing here is that we consider also odd isomorphism. So V and reverse V modulus.
What is VZ again? What is VZ?
VZ is a BC burst.
BC ghost.
But vacuum has usually even parity, but
I'm
as a
telling you,
representation, we can.
Not many people familiar here with VC ghost.
Oh, sorry about that. I thought yeah. I should spend much more time here, but yes. That is except algebra. Associated with and other name is BC groups.
Yeah.
Okay, so this is a kind of the easiest answer to understand the representation theory, meaning that we classify the simple modules and understand the tensor product decompositions. So this gives us an answer. And actually, so I just presented here to the rational case where we consider the very specific levels. But actually, this construction works almost all levels, where we don't have a kind of big nasty things where which I don't care during my talk, and so we can have a much better statement for almost all levels. Things that the correspondence goes much deeper. I'm saying that if we consider representations where we have a so-called weight conditions, where J0 in the Heisenberg, as a Heisenberg representation, it's decomposed as a Fock modulus. And here, and we can consider similar representation for affine SL2 and weight conditions. And then it decomposes into a certain congruence subcategories, which I call a block. And this is a eigenvalue of the highest weight of Heisenberg up to the eigenvalues appearing in the VO itself. So we have a kind of ambiguity, but we can have a decomposition like that. And
sorry, what is this decomposition?
So highest weights decompositions eigenvalues.
X to Z0.
Values, but up to the eigenvalues of Virasoroid, super Virasoroid itself. Because we already have an ambiguity of that.
Okay, but again, this is not J0 in your.
But here J0.
It is the actual. Okay, it is the term. Okay.
Here we have similar decompositions. By the way, this was minus. And then we have a.
Wait, why did you put a minus at the top?
Just a superside minus and odd part, even part for the press. You can call C and D or whatever you like, but I just give just two names.
Okay.
Yeah. Here we have a bunch of categories parameterized by this class. So like this. These concept constructions we can generalize to modules by considering the Heisenberg representations, the coefficient space for the Heisenberg representations. So this gives us a bunch of functions like that, which I don't specify very much.
So what are these dots?
Oh, that is one of this category.
Say again?
Category. So one and I
category.
yes, just infinitely many, but I just visualize here. So to say that we have a lot of correspondence.
But here, as it's not simple quotient. It's the whole.
It's not a simple quotient, but we can restrict to a simple quotient.
Because here you were talking about simple quotient.
Yes, and this is we can restrict to a simple quotient because simple goes to simple mathematically, but yeah.
No, but simple quotient it's finite category, right? For
Oh, so wait, so
for levels, for integer levels.
all levels.
It is for all levels, okay.
Yes. So at some point, this is admissible, so much wide categories.
So when you take all levels, you don't consider quotients, right? Because there is no quotients.
Excuse me?
When you consider all levels, generic level, right? There is
No,
there is
all the levels, except for two levels actually.
simple-
Where critical levels and where Heisenberg degenerate. And that's two levels that doesn't go in this construction, but after that, all works.
Okay.
And if we start with a module, then we just tensor it with a lattice superalgebra and plugging out all the highest weight vectors, then we get the module on the other side, and maybe on the other side, and this gives us a equivalence of categories. This was found by Feigin and Semikhatov and Tipunin and 98, if I remember correctly.
You don't have two arrows going to the same one. It's
So we can change, we have ambiguity with these guys.
Ah.
To slightly go into different categories.
okay.
Yes.
If you draw cylinders on both sides.
Excuse me?
If you draw cylinders on both sides.
Yeah. Yeah, we can little bit compactify if you like. So this ambiguity is essentially the spectral for twist, if you know this diagram. And this is a enhancement at the level of abelian categories, but actually all the vertex algebra representation theory is talking about also the intertwining operators, and the fusion rule here represents such a compatibility. And actually, we can talk about the compatibility for intertwiners for all these generalities. How much do we have?
No, like I mean, few minutes.
Yeah, a few minutes. Okay.
5 minutes is okay.
Okay. Thank you so much. So we can enhance it. And the kind of the trick here is super zero and affine SU2 has a decomposition in terms of the Akop representations in the Heisenberg and plus and minus into charge. This is a Fock module of the Heisenberg, and the concept constructions saying that these coefficient space are always the same, but these two dressing by Fock representations are different. So especially this norm is different is all the problems. So concept constructions is
It's BK tensor BC. On
Okay,
that side. K tensor VZ or no?
great. Here,
Second line,
second line here.
left hand side. Is it just VK?
Yeah, yeah, okay, yes.
Just VK.
Yes, I just,
Tensor VZ.
yeah, it's a
Last time
two.
you talked about tensoring VZ.
Yes, so I'm talking about here. So replacing this Heisenberg is exactly tensoring with this lattice and take the coset. So this is a whole trick of this coset construction, and we can rephrase it as a certain D algebra cohomology of this affine D superalgebras, which by using a so-called higher differential operator for C star. We have a shift, but yeah, let's forget about that. And this gives us a bunch of informations. And if we take the representation, then it gives us a functor and things that maybe fit me right. So this is a replacement of the coset constructions, but it gives us all the compatible properties of intertwiners and modules that was missing in this formulation. And this is a kind of magic that we can use for huge family of W-superalgebras that contains the super-conformal algebra that I started with. And this one. Quick. And then myself and Sato. So we have a represent plus K bar. So it's an isomorphism to the affine subcategory to the super-Virasoro category intertwines maps naturally intertwines. This is all the bare data in the conformal field theory that gives rise to the notion of tensor product going to the other side. An important part is this function is very explicit. So we can rewrite the correlation function from one side to the other. And this is a huge advantage because this huge category of affine set, for example, is quite wide and like character doesn't converge. So it's going to be a distribution and it is a physical thickness actually of the Thomas stock. But here we make the so the character typically looks like that or looks like that. But because of this changing of this to the super world, everything has a lower bandwidth or all the nice property will be satisfied on the other side. So it's a kind of regularization of the correlation functions to give us a nice properties of these huge categories. And I'm losing the time, but this functor can be generalized by replacing GL1 to arbitrary simple Lie groups, which gives us a huge amount of correspondence of this type between many kinds of W-superalgebras. That is the title of my talk. Thank you very much.
Questions? We have a question. So these equivalence functors,
Yes.
they preserve some kind of monoidal structure, or
Yes,
C lambda
exactly.
K are not monoidal, right?
Oh, so
For fixed lambda, they're not monoidal.
exactly. So a kind of point-wise things. So we can, for example, compare the associators, for example, and the trick here is if we have a intertwiners, then this is the other side of the intertwiners is a Fock intertwiners acting on this cohomology things, which means that each intertwiners is addressed by the Fock intertwiners. At the level of category, braided tensor categories, it's a change by using the abelian two cocycles. Yeah, because this is a pointed category and all the braided tensor category is realized by the three cocycles, yes. But this is when we have the braided tensor category structures. Actually, if we have a braided tensor structure in one side, then we can prove we have a braided tensor structure.
So is it, what is the group of simple objects in that point of part? Continuous group like system.
Oh wait, here.
Yes.
Yes, for the universal ones, yes.
System.
So it's a C-square and extremely huge. But if we restrict to a simple quotient, then this is going to be much smaller. And yeah, just finitely many. And sometimes we have a two category going to the same. So that's why we have a kind of tensor product in the fusion rule here over Z2. This kind of things appear. Yeah. But at the level of intertwiners, then this is a kind of ultimate statement.
Are they interesting tricocycles, tricocycles on C star?
Now is a kind of the good news for us actually, because we can standardly understand the complicated category if we want to work with lightly.
Okay, if no more questions, thank you.
Thank you very much.